So I guess this is lecture 18, right? So we are discussing inner products, which is just another name for scalar product. That you take any two vectors from your vector space and using this pair, you make a number. So when I write these curly brackets, that means now I'm dealing with a number. So with every two vectors, you associate a number, and that's a scalar product if it satisfies the properties which we wrote last time. And we were discussing this theorem, which is the Schwarz inequality. Now, as I said last time, these inner product or scalar product, we have distilled this from our intuition of geometric vectors. So that means whatever the knowledge we have about geometric vectors and the scalar products over there, we can translate them into a general, an abstract vector space and an abstract inner product on that abstract vector space, and hope that it still holds true. Obviously, we have to still prove it using the general properties of the inner products, but our geometric intuition tells us what theorems we can hope to prove over here. So this is the Schwarz inequality, and what does it say? For any vectors VU in a vector space, if I take the vector product, let me write it this way. The dot product, and then a dot product could be a positive number or a negative number. I make a positive number out of it by taking a modulus, then that number would be less than or at most equal to the norm or the length of the two individual products. And I also know when the equality holds. With equality holding only if one of them is a multiple of the other. So and how do I get this idea? I got it from this fact that for geometric vectors, if I take the dot product, for them, the formula for the dot product is the length of U times the length of V times the cosine of the smaller angle between them in going from one vector to the other. So this number, because cosine theta is less than 1. Well, actually, this is the range. So if I take the absolute value of cosine theta, that's less than 1. So therefore, U dot V, its absolute value has to be less than the length. Because when I make the U dot V, apart from length, I'm also including a number which is smaller than 1. So this is how I guessed it. And let's see if this holds for a general vector space or not. And from here, I can also guess when it would be equal. It will be equal if u and v are pointing in the same direction, because then cosine theta would be just 1 and I will have an equality. So how do I prove it? I don't have this formula, because that's not how I'm defining a dot product for a general vector space. I don't even have a concept of angle so far. So how do I prove it? So if I consider a vector u and then its projection, its vector projection, along v. How do I define the vector projection? We defined it last time, but let's write it again. So again, I'm giving it a abstract mathematical definition, but the idea is coming from here, from geometry. That if you have this v and u, the component of u along v is just, in geometry, is just the dot product of u along with v, and you divide it by the length of v. So v dot v is the square of the length of v. Is v square, because it's just v length time cosine theta. So that's what you usually do. You would do if they were just geometric vectors, times v. So v you can think of as length of v times a unit vector along the direction of v. So this whole thing then kind of, you can think of it as u length, v length, cosine theta divided by v length square, v length, and the unit vector along v. So the v lengths, they all cancel and you get the length of u times cosine theta. So it gives you the component of u along the v, and you make it a vector by giving it a unit vector. So that's the idea, that this object, if written for geometric vectors, would give you the projection of u along v. So you just give it the same name. Over here, you don't have this geometric picture, but you just construct this algebraic object made up of these abstract vectors, and you just say that, okay, let's consider this object and think of it as a projection, and then you hope that the properties which hold in the geometry will hold over here as well. So then I define the difference of u minus this projection. VV. Now I would know that if I consider this projection, let me draw it again. This is u, this is v, and this is the projection, vector projection of u along v. Then if I make this vector go from this vector projection to u, then this is just simply u minus this projection. right? So this is the projection. Projection times this vector is equal to u by head to tail rule. So this vector must be u minus the projection. And obviously, from this figure, it has to be orthogonal. So that's why I constructed this guy. And my expectation is that this z, which is the difference of u and its projection along v, should be perpendicular to v. This sign is used for perpendicular, and perpendicular is just the terminology which I have extracted again from geometry, and it literally means this in the abstract sense, that the dot product or the scalar product or the inner product of this z with v is 0. That's what perpendicular mean over here. So if this is true, if I open it up, I have this guy, and this whole vector, its inner product is being computed with v. So now I use the property of the inner product that is linear. In other words, you can break it up. So this u goes with v minus, this is a number. This is a number because these are inner products. These are already numbers. So the numbers come out. These numbers come out. And then you make the dot inner product of this vector with the next one. But this cancels with this, and you have a u dot v minus u dot v, which is 0. So we have proved that indeed the z is perpendicular to v. Now, last time we proved the Pythagorean law. We can use Pythagorean law or Pythagorean theorem, which was that if a vector is composed of a sum of two orthogonal vectors or perpendicular vectors. But for perpendiculars, I also use the terminology orthogonal. That's more commonly used. And use the symbol perpendicular. This is a symbol for orthogonal or perpendicular. That if two vectors are perpendicular, well, there's one this vector and one this vector. If you scale up vector by a number, it still remains perpendicular. Let me write the whole thing. We just proved this, that these two vectors are perpendicular. So we proved it last time, and again we guessed it, that if two vectors have an angle of 90 degrees between them, they're perpendicular. In other words, the scalar product is 0. Then we know that Pythagoras theorem will hold, and the length of this guy, of the sum, will be equal to the sum of squares of the individual vector's length. That this square would be equal to whatever this square times this square. That's just Pythagoras theorem. And we proved it last time abstractly. So if I use this and I get this is the length of this vector, because the length is a positive number, so you get a square over there. And this means now this guy this is just again let me use this color. It's just v square, and this thing, then this square is just v to the 4. So this implies that this equation becomes u square is uv mod square, and I have a v to the 4 and a v to the square upstairs, so I am left with v length square. Plus I have an extra positive term. Now if I throw this out, so I'm throwing out a positive number, so that would mean this left hand side would be now greater than this thing, because I threw away something positive. And I have something positive downstairs. I can take it to the other side without changing the inequality. And I get this, which is exactly the Schwarz inequality, which I had to prove. And also, if I come back to this equation, let's call it equation 1. From equation 1, the equality will hold. I threw something positive away if that something is actually 0. Hold if this length of vector z is 0. But that would mean only the 0 vector has 0 length. So z is 0. This vector is 0 vector. So that means u minus, I had this z was some number over here times v. This is 0. So that means u is some number times v. They are collinear. So I have exactly proved the Schwarz inequality. Now I have some corollaries from here. So I can write this Schwarz inequality like this. Being the length of the vector, which is just u dotted with u and the square root, is also called the norm. So I'll be using these terms interchangeably, norm or the length of the vector. So if I bring it down, then that's what it's saying. Now, in the denominator, you have positive numbers, but in the numerator, I can take the square root. So if I remove the norm, then I'll get that is this thing is between -1 and +1. If this thing is between +1 and -1, I can parameterize it. I can put it equal to something which takes values between +1 and -1, some function, and I can call it cosine theta. So because of this property, because of Schwarz inequality, I can define an angle. So this is the definition. This is the definition. Define an angle between any two abstract vectors. And what's the formula? The formula is the same. You take the scalar product of those two vectors and divide them by their lengths. Or in other words, for abstract vectors as well, I can write this formula. For any vectors with this definition. I have some other consequences. Well, let's derive one more, again using our geometric intuition. So if I'm given these two vectors, u and v, and I consider this sum, if they're not making a 90 angle, then triangle equality or the triangle Pythagoras law doesn't hold. But now I know that the triangle inequality holds. In other words, the length of the sum is less than, and the square is less than these guys. So how do I prove it? So this thing, whole square, by definition, it's just the scalar part of this vector with itself. Now I just open it up. So I get two norm squares and then a cross term, two cross terms. So this becomes, by definition, u length square plus v length square. And now over here, I use the property of the scalar product that it's symmetric. U scalar product with v is same as v product with u. So this becomes 2 times uv. Now over here, I want to throw this away in some way. But this can take positive or negative values, so I don't know what to do with it, except that I can use Schwarz inequality. And 2 times uv is less than or equal to uv. Even its modulus is less, but if its modulus is less, that means even if it were negative value, if I make it positive, even that is less than this. So if it's a positive number, it's definitely less than this. But if that number becomes negative, even that is less than this. So I can remove the mod, even that's fine. So this then becomes less than this, because this number is less than these two dots. So I get this. This just becomes whole square, which means well, there were no squares here. That their length sum is more than this sum. And when will it be equal? You know that it will be equal if they are collinear, because then their sum would be just, you keep going from one to the second. Now let's just take some examples of these theorem working in some abstract spaces. So consider P3, which in Book's notation, polynomials of degree 2 up to 2. And we had defined a scalar product over these guys. We needed some numbers to define it. And you can choose any number. Each set of numbers will give you a different scalar product. There can be many scalar products on a vector space. So I choose these numbers to define scalar product between two vectors, which will be just two polynomials, would be just the first polynomial. Let me write them as polynomials. The first polynomial evaluated at y1 times second polynomial evaluated at y1 plus first polynomial evaluated at y2 multiplied with second polynomial evaluated at y2 and so on, and you just do the sum. So that's the definition of the scalar product. Now, if I compute the norm of, I want to check what is the length of this polynomial, very simple polynomial, x and x square. 2 from the basis. So x length square is x scalar product with x, which is simply -1 times -1 plus 0 times 0 plus 1 times 1. So it's 2. And I can write the length as under root 2. What's the length of x square? Square of the length of x square is -1, x square evaluated at -1. So it's -1 square, -1 square, plus 0 square, 0 square. So it's 2. So x square's length is again under root 2. And what's the scalar product with each other? So it's minus 1, x evaluated at minus 1, and then minus 1 square. So this gives you 0. This means x and x square are orthogonal in this scalar product or in this inner product. Now we can check that the triangle inequality holds because they are orthogonal. So the triangle, not the triangle, the Pythagorean should hold equality. If I do x plus x square norm square, so it would be this polynomial a 0, so it's 2, 1 plus 1, 2 times 2 plus 2 times 2, 4, 1 plus 1, 2 times 2, 4 plus 4 is equal to 8. So it's just so the Pythagoras holds because these were just the norms of these. Now, if I consider, so that means again how this is useful. If I consider this, I have just found out that the angle between x and x square is 90. They are orthogonal. So I can mentally think of them as pointing in orthogonal direction in some abstract space. So that means if I consider a polynomial like this, so it would be something like going along the x and then adding to it 2x square. So the sum would be this vector. And now I can see, so this vector would be representing this polynomial. Now I can see that the angle between this polynomial and this x should not be equal to 90 or 0. There's some finite angle between them, and I can check it. So if I compute this, that is equal to -1 times -1 plus 0 into 0 plus 2, 1 square plus 1 into 1. So I get 2 minus 1, which is 1 into -1 plus 3. So it's 2. So they are not orthogonal. I can compute the angle if I know the length of this new polynomial. So the length is minus 1 square minus 1 square. So this is equal to 2 minus 1, it's 1, plus 3 square 9 is 10. So that means the cosine theta is the scalar part between them, which is 2, divided by the length. So this was square. And the length of the other was under root 2. So you can compute the angle by doing this. Let's take another example. This time, let's consider this space of matrices. We had defined the scalar product as this object. So this gives me, first I have to make a product. I take A transpose, so it gives me 1, 2, 3, 1, and B as it is. Because this combination, it gives me a number and it fulfills the properties of a scalar product. That's why I had to find it this way, but you can consider many others. Anyway, so when I do this product, I get this matrix 1 minus 2 minus 1, 1 plus 4, 5, 3 minus 1, 2, 3 plus 2, 5. So the trace is just the sum of the diagonal entries. So it's 4. So the scalar part is 4. And if I compute the length square of A, it's just this. One, two, three, 1, and 1, 3, 2, 1. So I get 1.1 plus 2.2, 1.3 plus 2 times 1, 3 times 1 plus 1 times 2, 3 times 3 plus 1 times 1. So when I take the trace, it's just 1 square plus 2 square plus 3 square plus 1 square. So it's just the square of the each entry. Because remember, we had this thing, trace of A transpose B, we had written in another way as sum of the corresponding entry, product of the each entry and summed. Similarly, B square then gives me 1 square plus 1 square plus 1 square plus 2 square. No, it weighs B. Yeah, it has 1, 1, minus 1, and 2. So it gives me this, which is simply 7. So Cauchy-Schwarz, I can check the Cauchy-Schwarz. Or we have been just calling it Schwarz. People sometimes call it Cauchy-Schwarz as well. That the scalar product, its norm, should be less than the length, which is true. Now let's take another example just to tell you that the scalar products, you can choose many different scalar products on the same vector space. So a non-standard inner product on Rn. We had already defined one where we just multiplied and summed the corresponding components, but now define another one. So pick any vector fixed vector for a fixed W, which is such that each entry is positive. Each component is positive. You're not picking any vector with any negative numbers in its component. So fixing this, we can define a scalar product. V U. So before we had the corresponding things were being multiplied and you were summing. But now you can include this fixed vector over here, the components of this fixed vector. So this is called the weight. And for each fixed vector, you are defining a new scalar product. So you have an infinite number of different scalar products. All you have to do is check, is this inner product? Well, first thing is it should be symmetric, which obviously it is, because if I replace V by U, the formula stays same. So yes. Is this thing positive definite? So this is Vi square times Wi, since W's are all positive. So this is actually greater than or equal to 0. And it's equal to 0 if and only if Vi are 0, because W's are not zeros. W's are all positive. So the second condition is also fulfilled, because you have to check that the norm scalar product of V with itself has to be greater than 0 and equal to 0 only if the vector itself is 0. And this one is also holds, you can very easily check. Hence, it's a scalar product or inner product. So now, if you pick a vector from Rn, their lengths will be different under this new scalar product. Their angles between them would be different under this scalar product. But you are assured that all the theorems you have derived, the triangle inequality, the Pythagorean theorem, the Schwarz inequality, they will still all hold. because those we derived not taking any special form for scalar product, but just these three properties. So that's the idea, that you can define new scalar products and still use your geometric intuition to deal with them. Let's move to, once you have a scalar product, define the scalar product on a vector space. We already had these things called the basis. They're already always given in a vector space. But once you have a scalar product, you can consider some special bases, which are called the orthonormal basis. So what is it? Let's start from here, that if you have a set of vectors, let's say m vectors, and they are all orthogonal, mutually orthogonal, that is, their inner product is mutually zero. What do I mean by that? I mean that if I pick any two, then the scalar product is zero. Two different ones. So if this is true, then you call them, then they are an orthogonal set. And on top, so this is orthogonal. But if the scalar product with themselves, or in other words, the length square of them, is equal to 1, then they are called to be, they are normalized. Such a set would be called an orthonormal set. Which is orthogonal as well as normalized. So for example, I can take some examples. In R3, if I pick these two vectors, this is an orthonormal set. This one I have just checked. You should check it on your own. This is orthogonal, but not normalized, because their lengths are not 1. Well, actually, I can quickly compute what are the lengths. I just have to square the components and add them. So its length is under root 3. Its length is under root 9 plus 4 plus 1, 14. Its length is 25 plus 16, that's 35, 41, 42. So they were not normalized, they're not normalized, but I can, if I'm given an orthogonal set, I can very quickly normalize it. How? I replace these by these ones. I divide them by their length. Multiplying by any number does not change the orthogonality of two vectors. So if these things, these two guys, they're orthogonal, that means their scalar product is 0. If I multiply them by any numbers, so multiply first by alpha and second by beta, I know that by properties of the scalar product, these alpha and beta are going to come out. And since UV are orthogonal, I get a 0 from here, so they still remain 0. So changing the lengths does not change the fact that they were orthogonal, so they remain orthogonal. But by scaling with this length, now the norm will come out to be 1. So for example, if I take this, its norm or length is, this thing stays out, and then I do this, so it's still 1. Or you could write it this way: 1 over under root 3 square plus 1 over under root 3 square plus 1 over under root 3 square. 1. So in this way, I can very quickly normalize them. Now suppose, by the way, the ones which I gave you originally, you could write them as like this, ij. Now there is a very useful quick fact, or I can call it a theorem. It's just 2 lines. Is this phenomenal fact that no matter what kind of scalar product we define, but a set of orthogonal vectors, they don't even have to be normalized, as long as they are orthogonal, is linearly independent. So if I pick these m vectors and they are orthogonal, we have to prove they are also linearly independent. Doesn't matter which scalar product you use, they will always turn out to be linearly independent. So I write, to check the linear independence, I write this thing. This is not very visible. Equal to 0. So pick any one of them, say Vi, where I is between 1 and m, and take inner product with above equation. So I take an inner product with the vector on the left hand side and with the vector on the right hand side. When I take it with the vector on the left hand side, it's just a vector. By the properties of the vector, the inner product, it breaks. Then you will have, at some point, you will encounter this Vi. जो भी आपने choose किया था, if you had chosen like I is equal to 6, so you will encounter V6 times V6 and so on. And on the right hand side, you are taking the inner product with the zero vector, which gives you 0. Now, since they are orthogonal, all of them start becoming 0, except for this one, Vi with itself, which gives you the norm of Vi squared. And this is 0. But none of these vectors were assumed to be non-zero vectors. So none of these, if they are non-zero, their norm cannot be 0. So this implies that Ci is 0. But this is true, but this can be done for all I. So this would be true for all I. So all Ci are 0. This implies the vectors are linearly independent. That I assumed that the linear combination is 0, and I was forced to conclude that all the coefficients are 0. That the linear combination can be 0 only if the coefficients are 0. So that means that if they're orthogonal, then they are linearly independent. So then I have a very quick conclusion. Now I come to this orthogonal basis. If I have n orthogonal vectors, if I have a set of n orthogonal vectors, vectors in an n-dimensional vector space, then what I have is n linearly independent vectors. But I know if I have n linearly independent vectors in an n-dimensional vector space, then they must form a basis. This we have done long time ago, and it should be by now ingrained in your brains. That means we have an orthogonal basis. They form a basis. And we have an orthogonal basis. What's an orthogonal basis? It's a basis, and each vector in them is orthogonal to the others. So for example, let's take some example. Well, pictorially, if I'm in R2, I know that these two vectors, they form a basis because I'm in R2, it's two-dimensional. These two are linearly independent, so they form a basis. But they're not orthogonal because the scalar product is not 0. There's a certain angle which is not 90. But if I consider these ij, They are linearly independent as well, but this time they are orthogonal as well because the scalar product is 0. So these are linearly independent but not orthogonal. So it's a basis but not an orthogonal basis. This is a orthogonal basis. I can form many other orthogonal bases. So if I start with this vector and take this vector, this is also, they are also linearly independent and orthogonal, so it's a orthogonal basis. I consider this one I, and let's say 3 times j, they are also orthogonal, and 2, they are 2, so they are a basis. It's an orthogonal basis. This one, since their lengths are 1, is a orthonormal basis. If you are given an orthogonal basis, you can very easily make it an orthonormal basis, as we discussed just right now. Just have to scale their lengths. So let's take another example of an orthonormal basis in R2. So for any theta, define these vectors. I've given you 2 vectors, and it works for any theta. You can put any value of theta and compute what these numbers are, just leave them like this. Then these vectors are actually orthogonal, because if I compute the scalar product, what do I get? Cosine theta, multiply the corresponding components and add. This is 0. And if I check the length, the length of the first is 1. Similarly, the length of the second is also 1. So it's a orthonormal basis. And orthonormal bases have a very nice property that you can expand the vector in terms of this basis using scalar products. So if now I'm writing up to n because it's a basis in n-dimensional space. If is an orthonormal basis, and I write a vector in terms of this, it's a basis, so any vector can be written as a linear combination. Then you can find these coefficients which will make up any arbitrary vector very easily. These Ci's are just the scalar part of the vector whose expansion you are trying to find out with each of this ui. You can see it very, very easily, because over here, if I take a scalar product with let's say uj, in this equation, this comes out. All of these are 0 except when I is equal to j, and then it's equal to 1. So you are left with Cj is equal to Uj. That's what I did over here. And so very easy to compute the expansion of any vector in terms of an orthonormal basis. And scalar product of two vectors VW, if you know the expansion, it's just this, where these are the expansion coefficients in this basis. V and W are two vectors, so both can be expanded in this basis. That's what I have done over here. And whatever the components turn out to be in this basis, you just compute the ordinary scalar product as if they are living in Rn. Because remember, we discussed this, that in terms of expansion, in terms of a basis, every kind of vector can be written as a column. So it turns out that any vector space, any scalar product, in terms of an orthonormal basis, looks like just the scalar product of ordinary column vectors. Let's see an example of this. So consider the vector in R2. X1, X2. And I expand it in terms of that orthonormal basis, which I had just given an example above. So how do I find? The question is how to find A and B. So my formula above said that A is going to be equal to the scalar part of this vector with the basis vector V1, which is cos theta minus sin theta. And B is going to be again with the other basis vector. So it gives me x1 sine theta plus x2 cosine theta. So that means I can very easily expand this in this basis as x1 v1 v2. And so orthonormal bases, you can pictorially always imagine them. Like if you are in 3 dimension, it's like I, J, K. Or a rotation of this, a rigid rotation of this thing. This will also work. I dash, J dash, K. Rotation around K axis or rotation around I axis, or in any way. you like. I think let's stop here.